Okay, folks, this is the last of the equilibrium chapters. This one is actually in many ways, this is actually the simplest of the equilibrium chapters because you realistically in this chapter won't have a number of the mathematical equations and terms that you had to deal with before. So, in many ways, again, because you have more information, you have less work to do mathematically. Now, this is going to be your solubility and complex ion equilibrium. And so, as you could probably guess, we are now going to be working on solubility. It's very similar to what you've seen before, but keep in mind we're not really going to be doing acids bases right now. We're going to be doing solubility instead. That's dissolving salts, right? Okay, this one's actually very short compared to the other ones, and the reason this is so much shorter is, again, we've already covered almost all of this topic, really. We've done a pretty exhaustive job talking about equilibria, how to manipulate equilibria mathematically to determine different values in that equilibria, including and up to the equilibrium constant and expressions. And we've even talked about when we have common ions and everything else. So don't forget, this is building off of those previous chapters. So that's actually one of the killers in this chapter. This chapter is actually, of the equilibria chapters, probably the easiest chapter of them. But because it depends on some of the previous things that you may have just glossed over because you were trying to learn so much other stuff, this chapter tends to be one of those that people that caught up and were kept up with previous chapters do well. People that didn't quite manage to keep up with those previous chapters and understand them find this chapter to be just, icing on the cake, if you will. All right, so equilibria. So when you have a typical ionic solid dissolves in water, it's going to separate into its cations and anions. And we see an example of this right here. We have calcium fluoride. It's a solid. We put this in water. And how it dissolves in water is by separating into its cation, which is calcium 2 plus, and its anions, which is 2 F minuses. That is 2 separate F minuses. And so these are aqueous, of course. That means in a water-based solution. So the ions that are formed whenever you dissolve one of these calcium fluorides is calcium and fluoride, right? And so for each of these calcium fluorides that we dissolve, we will make 3 of these ions. 1 calcium, 2 fluorides. In this reaction, when the solid salt is first added, there will be no ions present. When you add the solid salt, it will then dissolve through this ionic dissociation, or this would actually be the dissolution, if you will. As this dissolution or dissociation occurs, you are actually going to see that your concentration of your calcium and your fluoride will go up until you reach your equilibrium point. Now, again, notice I keep talking about equilibrium. So we're only looking at the reaction going in one direction right now. That's that we've added calcium fluoride in here, and it's separating out into the water as the individual ions, right? So of course, if the calcium and fluorides are floating around in water, they can bump into each other, they can recombine, and they can actually form the solid again, which would be your calcium fluoride solid. And this is actually what happens if you've ever dissolved a salt or dissolved like salt water and it was hot and so everything dissolved, right? You may have done this with Epsom salt. That's probably the most common one that people do. They put Epsom salt into a hot bath. And so it was all dissolved. You didn't see any solid. And then as the bath cools down, what happens? Well, some of the Epsom salt is going to recombine, form its solid, and precipitate out of the bath, right? Leaving you with the solid Epsom salt in the bottom of the bath. And that's what you're seeing here. Yes, this can establish an equilibrium in where you have your calcium fluoride dissociating and going into solution, and then the ions that are in solution, when they impact each other, they combine back together and again form your crystals. And again, that would then precipitate out and eventually would settle to the bottom as a solid. So remember, that is because these equilibriums are always dynamic equilibriums that we've been talking about. And so this is a sign that you have reached the saturation point. Now again, notice that I've actually given you a definition within this, that the saturation point is where you will have some of your ions in solution that will precipitate out. So to be a saturated solution, you have to have a small amount of solid that is precipitating out. At least one crystal. At least one molecule, okay? All right, now, the equilibrium expression for this is going to be, you have KSP right here, which I haven't given you a definition for that. It's a solubility product. And that is going to be equal to products over reactants, right? Just like every other K. And so we have our product here. There's only one in front of it, so this is calcium to the first power. This right here is the fluoride. Remember that the concentrations were always to the power of their coefficients. So in this case, there's going to be 2 fluoride. So you're going to have the concentration of the fluoride to the second power. One of the things that people start getting messed up on, because you guys spend so much time acid bases, and all of these were to the power of 1, a lot of people forget by the time they get here. And they want to put this 2 inside here, or they want to not put the 2 at all. Remember, you don't put 2 in here when you're doing just the concentration. It's just the concentration, okay? That has nothing else to do with anything else. Just put concentration of fluoride. Now, this is then to the power of its coefficient. And so you put the 2, and this is the power right here. Why do I not have a denominator? Well, think about it for a second. Okay, hopefully you looked up here and you went, well, that's a solid. It's pure solid. And so that means it goes to unity, or another way of saying that is this concentration is actually part of this KSP right here. It doesn't change because it's a pure solid. It's a constant. All right, so the solubility product constant. This is KSP, and the SP tells you solubility product. The K is for constant, right? And so this is going to be your equilibrium constant, or your equilibrium expression constant, that represents the dissolution of an ionic solid in water. This is going to represent dissolving salts. Now, this is also known as the solubility product, and you're going to see that quite a bit. Chemists have a tendency not to want to say all the words and cut things short. And so you will see that quite a bit, actually, if you actually go out into professional field and such. Just because you don't have to say constant, constant, constant. Everybody knows the constant. All right, the solubility equilibrium is going to be unaffected by the excess solid formed. Again, that concentration of solid is not in there. So it doesn't matter how much solid you have here. The size of the particles present is also going to affect your solubility equilibrium. The differences between the solubility of a given solid and solubility product. Well, the solubility is an equilibrium position. So when you talk about the solubility of blah salt, the solubility of aluminum chloride, the solubility of iron chloride, these are positions, these are concentrations you could have before you would start seeing precipitation. Okay? Those are not the solubility product. The solubility product is independent of the position, of the concentrations. The solubility product is an equilibrium constant. Has only one value for a given solid at a given temperature. So at 25 degrees Celsius, it doesn't matter how much aluminum chloride you have in there. It doesn't matter what concentrations you have. All that matters for a solubility product is that it is 25 degrees Celsius and that is aluminum chloride. That's it. All aluminum chloride solutions at 25 degrees Celsius have the same solubility product. They can have different equilibrium positions or solubilities. Okay. Now, let's calculate the KSP value for bismuth sulfide, Bi2S3, which has a solubility of, notice this is not solubility product, it's solubility. So this will be a concentration. This concentration right here is 10 to the negative 15th at 25 degrees Celsius. So we have a solubility here. We need to get the KSP from it. And right here is our formula. Whenever we dissolve salts, they always have to break apart into their individual anions and cations. This is one of the things I find people have the most trouble with right here is many students just do not remember or never bother to remember their polyatomic anions and cations. This is something from General Chemistry 1 that you should have seen so much that it sort of just ingrained in you over time. But if you don't remember your polyatomic anions and cations, things like sulfate, SO4, nitrate, carbonate, those sort of things, those are all polyatomic anions, then you may want to go back and review, okay? And it's in your book. You can just go back and review. There's a small list of them, and they all have sort of the same looking formula. So they're actually easier to remember if you remember them in groups. Okay, so let's go ahead and try to solve this problem. First off, you need to understand the definitions I've just given you. So KSP is again going to be a, well, equilibrium constant. It again has an equilibrium expression. How do you get that? Well, you're going to have to write the dissolution or dissociation of this ionic solid right here. And so you're going to have to write this breaking up into its aqueous ions. Now, the other definition you need to understand here is what is solubility. Now, solubility, many students get stuck on this. They just don't get the definition of solubility. So what solubility tells you is solubility is the equilibrium position, okay? Solubility means that you are having this backward reaction occurring. So solubility is the equilibrium position here. That is your equilibrium concentrations. Okay, so your system initially just contains water and solid Bi2S3. This Bi2S3 is going to dissolve like so. And notice we just break this apart. So we go Bi, we put 3 plus there, it's cation, that's the charge that has to be accounted for. By the way, how you can do the charges on these. I would always select the one I know better. Typically that is a nonmetal, just because the nonmetals have a nice, very easy pattern. Just count over to the right to a noble gas. And so sulfur is 2 steps from a noble gas. That means it has a 2- charge. This is not a polyatomic anion or cation right here. These are just monoatomic, single atom ions. And so you're going to have 3, that's the 3 right there, is going to be your coefficient. You're going to have to make 3 of these every time you break one of these apart. And you're going to have sulfur, and this is going to have a 2- charge. You'll notice that the total charge here is 3 times 2-, so a -6. That means that bismuth here, Bi, needs to have a total charge for those 2 Bi's that would total to a +6 because there is no charge right here. So that charge right there is 0. That means this is neutral. Now, this Bi right here thus has a 3+ charge. 2 3+ charges would give you a +6 charge. Again, the 2 comes from right there. You have 2 Bi's every time one of these breaks apart. This is an equilibrium, of course. That's what the solubility actually means. So when you are at the solubility point, which would be where you have some of these combining back together to form solid, then you will have this equilibrium. Notice that if you did not have a high enough concentration of these for it to reach its solubility point, then you would never actually make solid. You would just keep everything dissolved in solution. If you've ever put salt in water before, and eventually you get enough salt in there that the solid just, actually usually if you pay attention, when you're putting the salt, NaCl, in water in your kitchen, if you pay really close attention while you're putting it in there, you'll see that the salt that you're putting in oftentimes actually dissolves at the top, and you lose track of it, and then somewhere in the middle to the bottom, it'll actually reform, and that's actually NaCl from the solution forming into the solid crystals. Anyways, so when you reach your solubility point, that's where you'll have solid coming out, and you'll see solid crystals. So your equilibrium expression here is going to be products right here. You don't have to put any reactant because the reactant in every single solubility is always a solid. So it's always a pure solid. You never have to deal with it, which is nice. You don't have any denominators now. So your KSP is going to equal your Bi3 plus ion to the second power. Again, that's the coefficient. Your S2 minus ion, concentration, to the third power, which is its coefficient again. So when you started this, when you started adding the solid, you will have none of these ions present in solution before this dissolves. And so your initial concentration of both of those will be 0. So the equilibrium concentrations of these ions can be determined using the solubility. And the solubility, the amount that dissolves to reach equilibrium, which is called the solubility, is 10 to the negative 15 in this case. So what we do is we look at 10 to the negative 15, and that was the concentration of the salt. That's not really an accurate statement, but it's a shortcut because you should know enough by now to be able to get the real meaning of that from that statement. So you have 10 to the negative 15 molarity of this salt, right? You should be able to tell that this is chapter 3 of general chemistry, that 10 to the negative 15 molarity should give you twice that number of Bi ions at equilibrium. So that means that 2 times, because every one of these you have 2 Bi's, you are going to get 2 times 10 to the negative 15. The S's, there's 3 of those for every one of these, and so you're going to make 3 times that number right here. And so that is 3 times 10 to the negative 15 molarity for the sulfide concentration. Those will be your equilibrium concentrations. So your Bi plus the initial Bi, which is 0, plus your change is going to be that 2 times 10 to the negative 15. Your concentration of sulfide at equilibrium is going to be 3 times 10 to the negative 15 that you just found. Again, those are your solubilities. Now, you can go ahead and plug those in and just do the math for your concentration of Bi. You go ahead and plug that value in. And for concentration of sulfide, you go ahead and plug that number in. Now, the math on these can be a little bit of a pain if you don't use a scientific calculator. What you do is you take this, you can distribute this power through. And so you would take 2 to the second, which would be 4. You would then take negative 15 times 2, so that would then be negative 30. And you do the similar thing right here if you want to try doing that on paper rather than a calculator. But of course, if you do it with a calculator, just be very careful that you get your parentheses in the correct places and do not assign the wrong powers to the wrong things. That is one of the mistakes that I actually see the most for these problems. So 1.1 times 10 to the negative 73 is going to be your KSP. Notice that KSP is ridiculously small. And that's actually quite, these have a really incredible range in solubility products. You can have negative 70s, negative 90s, hundreds. You can also have large values. They have a very, very large range, as you probably would surmise, because there's a very large range of solubilities. This is an exercise you can attempt to see if you know how to solve these problems and you understood what we just did. And that would be its KSP if you did this problem. Not that you really need it, because I've given you problems you can do on mastering. Now, the interactive example that we're going to do next is this right here, which is the KSP value for copper 2 iodate, which is the formula, is 1.4 times 10 to the negative 7 at 25 degrees Celsius. So we're then going to calculate the solubility at 25 degrees Celsius. So again, what did I actually say to you? Solubility is equilibrium position, isn't it? So I've asked you to calculate the equilibrium concentration of this entire salt complex right here. Okay, that's all you have to do. It's actually the same problem you've been doing. I don't even know how many times I've had you guys do this problem by now. It's a lot. You guys have seen me do these problems a lot of times. I don't even want to know exactly how many attempts you've made and everything else. So a lot. You've definitely done this a lot. Right, so the system is initially going to contain water and solid copper iodate. This is going to dissolve according to this following equilibrium again, which is right there. So again, this is a polyatomic anion right here. What that means is the iodine and the oxygens actually have covalent bonds between them. So these will not break apart. These IO3s will stay together as a single ion. And so your copper, how do you know it has a 2 plus charge? Well, it actually told you that copper with the Roman numeral 2, that was its charge. So you don't even have to do any work here. So that's copper 2 plus. The iodate right here, it actually told you it was a polyatomic anion too, because it called it iodate, right? As if it was one word. A big hint, that's a polyatomic anion. So you take this IO3, and that's going to be a single ion. Now, how do you get this charge right here? Well, if you don't remember what an iodate charge is, which is fine, you can just take the copper 2 plus charge. There's 2 of these iodates, so this has to have a negative 1 charge for each of these, because these charges have to balance to 0. Alright, so you have 1 copper for every one of these are made that you have dissociated. And for every one of these salt complexes that you have dissociated, you're going to have 2 of these iodates. That's what that 2 behind the parentheses means. Alright, now, this right here is going to be your KSP expression. So your solubility product expression, or another way of saying that, of course, is your equilibrium expression, just like we've been saying all this time. This again is going to be to the first power because that's the coefficient right there. This one's going to be the second power because it has that coefficient right there. So let's find your solubility of your copper iodate. We need to find these equilibrium concentrations then, don't we? So the next thing we can do is okay, so the normal way you've probably gotten so used to, and hopefully you haven't gotten so used to it that you think you just plug that in and you just do it. Instead, hopefully you have gotten, okay, this is easy, rather than doing it formulaically like a parrot or a machine or something. Alright, so the normal way we would do this is by specifying our initial concentrations, typically before any solid has dissolved, and then we would define the change required to reach that equilibrium. In this case, we do not know the solubility. So we will assume that we have X moles per liter of the solid dissolves to reach equilibrium. And the 1 to 2 stoichiometry of the salt would mean this. So for every one of X of these, this salt complex here, we would form a single X of the copper. And we would form 2X of the iodate. Again, that's just your stoichiometry, right? For every one of these, you would form one of these. For every one of these, you'd form 2, which comes from right there, of these. All right, so we can then plug those in. So our initial concentrations would be 0. Our changes have to be those X's, right? And so at equilibrium, we are going to end up with X for our concentration of copper here, and 2X for our concentration of iodate. We plug those in. We go ahead and do the math. This math actually, as long as you understand powers, is quite simple and straightforward. All you do is, again, distribute the powers. So 2 to the second is 4. And that's where that 4 comes from. X to the second is x squared. Multiply by another x, and that would be x to the third. Okay, so we have a KSP value that we were given. This is equal to 4x cubed. So we divide over the 4, which gives us that value right there. We then take the cube root of that, and that will give us our concentration for X. Now, notice right here, by the way, if you want to do a cube root, but you're having trouble getting the root with an X that you can fill in, note that you can just do this. You can take this value right here and take it to the 1/3 power. That's the same thing as a cube root, okay? Now, this right here, 3.3 times 10 to the negative third molarity, that is your concentration for that X. Well, the concentration of X is the same thing as the concentration of the copper. It's also the same thing as the concentration of your entire complex, because remember, the copper, there's only one of them. So it's a 1-to-1 ratio between your salt and the copper. So this is the concentration or your solubility of your solid copper iodate. That 3.3 times 10 to the negative third molarity, that is your solubility, that's the answer. All right, so this is an exercise again that you could test your ability to do the previous problem on your own and see if you understand how to do it. You don't really need these exercises. This is something I've kept in here in case you want a little extra work, but this was before I started using OWL, so yeah. You have plenty of problems that you can try and attempt. So the relative solubilities. One must be very careful in using KSP values to predict relative solubilities of a group of salts. So we have some possible cases here. Salts being compared produce the same number of ions. So if you have KSP values, these cannot be compared to determine relative solubilities. Salts being compared produce varying numbers of ions. So your relative solubilities cannot be predicted using KSP. So what I'm trying to say here, which I guess I end up taking a somewhat relatively circuitous route, is that, remember, this is your solubilities right here, right? This is what we're ultimately talking about. So your KSPs, when you look at this, remember that the concentrations are going to have powers, which are their coefficients, right? And so if you have KSP for two things that has the same number of ions that are splitting apart, you can compare those. That's going to give you a reasonable comparison, which will mostly tell you which one's more soluble. The larger the KSP, the more soluble it is. So if you were comparing something like NaCl, NaF, lithium fluoride, If you're comparing those three salts, you could just directly look at their KSPs. The one with the largest KSP is the most soluble. The one with the smallest KSP, that's the least soluble. There you go. No problem. And that's because they're going to have, well, lithium to the first power and fluoride for the first power. Or they would have sodium to the first power and chloride to the first power. They'll all have the same powers here. They'll all have the same factors. Now, this is going to break apart very quickly when you start trying to compare lithium fluoride to something like copper iodide here. That's because you have a power of 2 here, right? So you have an entire another power in here. This is going to completely wreck your comparison. The more different they are, the more the KSPs will not be able to be compared. Okay, so keep that in mind. This is not like acids where you can just directly look at the Kas and go, oh, this is stronger acid, no problem. The KSP, because they have different amounts of ions that they can dissociate in, because we have so much variety in the salts, they can't just be compared with no understanding. Okay? They have to have the same number of ions that split apart. Okay, so you remember the common ion effect, and I kind of alluded to this when I talked about the common ion effect last chapter, but the common ion effect is not just something that applies to acids and bases. It really applies to any equilibrium. In fact, it's just an application of Le Chatelier's principle, right? So the solubility of a solid will become low when the solution already contains ions common to the solid. So right here we have 2 dissolved solids. See that? Both of these were clear before we poured them together. Now what's happening here is that they have an ion that is common between them. So we have a potassium chromate solution that's being added to an aqueous silver nitrate. This is forming our silver chromate in this case. All right, the more astute of you may notice that we have our potassium chromate, silver nitrate. They do not have common ions in effect. Apparently, I ended up grabbing the wrong figure and caption. Oh, good God. But it does give me the right. It does look nice. It looks beautiful. Anyways, that's not actually an example of the common ion effect, okay? Sorry about that. Oh, man. So, if you add 2 things where the ion in both of them are common, this can reduce the solubility because you will have an initial concentration of that ion, right? So when you do that ice problem, you'd have initial concentrations, just like anytime you talk about Le Chatelier's principle. If you were to add more of one ion, it would push the reaction, the equilibrium, to the left. In these cases, the left is always the solid, and so that would cause precipitation. Can't believe I did that. Man. All right, so let's go ahead and try an example of a common ion effect. This is actually a common ion effect, I promise you. So let's calculate the solubility of solid calcium fluoride, which has a KSP right here, in sodium fluoride solution. And this right here has the concentration of 0.025. So we're looking for solubility, so that's going to be a concentration of that calcium fluoride. And we haven't been given a KSP for this. And the reason we haven't been given this is extremely soluble. It's a strong electrolyte. If you ever want to do problems where you could do several of these different species and they all have KSPs near each other, that's something you can have a great time doing in analytical chemistry. And as anybody that's taken analytical chemistry with me can attest, it is great fun. And by great fun, I mean that they smile ruefully and they have this sort of pained look in their eyes while they smile, but they still say it's great fun. Anyways, you can do species that are 10, 20, 30, hundreds of different salts all combined together. That's how you figure out things like streams. Right, let's do the problem. So again, you have an initial concentration of fluoride, right? This is just like those buffer problems we did before. And that's going to be from right here. And so that initial concentration of fluoride will be 0.025 molarity. You are going to again be looking for the equilibrium concentrations of calcium and fluoride. And that is going to have your KSP right here. So the first thing you always want to do in these problems is, of course, figure out your major species. So before you have calcium fluoride dissolving, you have sodium fluoride in water. And those will be your major species beforehand. Now, the sodium doesn't really do anything, but the fluoride is actually a common ion with your solubility equilibrium for your calcium fluoride, isn't it? And so you have your calcium here, you have your fluoride right here, and you have your calcium. It will break apart or dissolve or dissociate as one calcium and two fluorides. All right, that will give you an equilibrium expression like so. Hopefully you can figure those out by now. If you can't, please, please, please practice. All right. So right here, this is that same initial versus equilibrium concentrations I've been showing you for half a dozen problems at least, probably closer to a dozen. And we have no initial calcium when we start this, but we have an initial concentration of that fluoride that came from the sodium fluoride, right? And so when we do the change, for every one of these calciums that's made, you're going to make two of these fluorides. Where do I get that number? Well, I get that from right here, don't I? Which again comes from right here. All right, so that means that at equilibrium, I'm going to have X concentration for the calcium, and my concentration of fluoride is going to be 0.025 plus 2X. I can then substitute those in to my equilibrium expression right down here. Note that this number right here is very small. This number right here is a lot larger than that number right there. And so I can assume that that 2x is going to be negligible compared to the 0.025, which is a much larger number. And so that addition, subtraction, anything like that would be negligible. You can go ahead and just get rid of this term right here, this plus 2x. All right, which will leave you like so. And so this is your KSP again, is going to be approximately equal to, the approximate is close enough, to x times 0.025 squared. Notice we need the squared, don't get rid of that, be careful, that's one of the things that a relatively small number of students, but still enough students that I'm warning you, have trouble with and sometimes try to get rid of these powers. Please do not do that. All right, so we then square this. We would then divide it over, and that would give us x equals 6.4 times 10 to the negative 8. We would compare that with 0.025. Is that much smaller, less than 5%? Yes, yes it is. And so that was a good assumption. So our solubility, therefore, needs to be, well, it's the same as that x, isn't it? Because that would be a 1-to-1 ratio with our overall solid, the calcium fluoride, right here. And so our solubility for that calcium fluoride is 6.4 times 10 to the negative 8th moles of solid would dissolve per liter of that solution. All right, so pH and solubility. Increase in pH. This decreases solubility, forces the equilibrium to the left. Decrease in pH increases solubility, equilibrium shifts to the right. If the anion X is an effective base, the salt, M of X, will show increased solubility in acidic solutions. So some of the exceptions here. Well, one of the exceptions is silver chloride. This has the same solubility in acid as in pure water. And that's because the chloride ion is a weak base. It's a negligible base. So no HCl molecules will be formed. Adding H plus ions to a solution that contains Cl minus ions does not affect the concentration of your Cl minus ion. This does not affect the solubility of a chloride salt. If the resulting H plus that anion would be a strong acid, it will not increase the solubility. Okay? The reason that most of the time that you decrease pH increases your solubility is most of these resulting acids will actually be weak acids. For example, here we have fluoride. If we combine that with H+, that would give us HF, which is a weak acid, which will mostly stay together, right? Which will mean we're taking out fluoride and making HF the acid if we add H+ to this salt. And that's actually why we normally increase solubility when we decrease pH. So anytime you would form a strong acid instead of a weak acid, so HCl, HBr, sulfuric acid, so SO4, those will not typically increase your solubility. Okay. So let's try another problem here. The salt AgCl is blank soluble in strong acid solution than in water. And so that is going to be equally. It won't matter because, again, that's chloride, right? HCl is a strong acid. It won't make it any more soluble. Which is the correct mathematical expression for the water molar solubility, S, in molarity of Fe3PO4 2? Okay, so notice these all have S's in them. So these are all going to be multiples of S. So what you need to do is you need to get your KSP expression. Again, how do we figure that out? Well, we just use this 3 and 2 right here, don't we? So this right here, this 3, will be this power. This right here, this 2, will be this power right here. Okay, so the next thing we're going to do is we're going to use that S as if it's a X, okay? I'm going to put an X in here. I'm going to let X be the molar solubility S, simply because S's tend to get lost when I try to have people understand equations. They look too much like 5s, right? And so people lose them and lose track. Anyways, this X right here, that is that S, okay? Okay, so I've put in here 3X because this is going to make 3 of these every time this breaks apart, right? And so I'm going to do 3X. This right here is going to be 2X because every time I break apart that salt, I'm going to make 2 of those. And so that'll be twice 2X for the concentration. All right, so then I do the math. I square these, and I cube these. And what I'm going to get is 3 cubed is 9. 2 squared is going to be 4. And so I do the 4 times 9. And then I do the x to the third and x to the second. Sorry. So this 3 right here, I I said 9, didn't I? That's 3 squared is 9. 3 cubed would be 3 times 9, which is 27. So that's 27 times 4, which is 108. And then you're going to have x cubed, x squared. You put those together, multiply those together, and you're going to get x to the 5th. Okay, you go ahead and finish this by putting an s here. And that will give you this answer right here, which is 108 s to the 5th. And so that just gives you a way to solve these problems without having to actually put any numbers in. All right, the two salts, silver X and silver Y, have very similar solubilities in water, but silver X is much more soluble in acid than silver Y. What can be said about the relative strengths of the acid HX and HY. Okay, so if one is more soluble than the other, the one that had the solubility changes, that so what we can see here, that one that the solubility changes more. So the X is more soluble in acid. That has to be a weaker acid than the HY would be. So what we can see here is this HY, the reason that this is not increasing in solubility as much is the fact that the HY is falling apart easier. The HX, on the other hand, is increasing its solubility more, and so that has to be staying together, so you're removing that X from solution. And that's why you can get that HY is stronger than the acid than the HX. All right, which of the following graphs best represents the plot of solubility, which is going to be on our y-axis, versus KSP, which will be on our x-axis, for a salt, MX, and pure water at constant temperature. All right, so the easiest way to think about this is you can actually use the equilibrium expression here to represent the relationship. So if you remember, the basic relationship is KSP equals the concentration of the cation times the concentration of the anion. And so those two concentrations can both be represented by X, right? And so what we get is the KSP equals the solubility squared, essentially, right? That means that if we solve that so that the solubility is by itself, and that square would be a square root of the KSP, wouldn't it? And so we would have the solubility equals KSP to the 1/2 power. The closest one of these to that relationship would be this one right here, B. So you mix two aqueous ionic solutions together and they do not react. To this mixture you add dropwise a third aqueous ionic solution. At first a white solid forms. As you continue to add more of the third solution, a yellow solid starts forming. Which of the following can you state with confidence? Okay, so you go through here. The first option is solubility of the white solid is greater than solubility of the yellow solid. Then you have solubility of the yellow solid is greater than solubility of the white solid. Okay, so we're adding in a solution, right? And you're making two solids. So which one would appear first? Well, the one with the least solubility is always going to appear with the lowest concentration added, right? Which means the lowest solubility one will always appear first. So the solubility of the yellow solid, so the yellow, if you remember here, the white forms first, the yellow solid forms afterwards. So the solubility of the yellow solid has to be greater than that of the solubility of the white solid, because the white solid formed first, whereas the yellow solid formed later. And that's going to have to be our answer right there. The KSP for the white solid is greater than the KSP value for the yellow solid. We can't really tell because we don't know their formulas, right? We would need their formulas to compare KSP values to their solubilities. All right, so you remember the Q's that we used before, and they were reaction quotient back when we were first introducing those? Well, they've come back and haunted us. All right, so again, in the solubility problems in this solubility chapter, it's great to be able to know whether you are, which direction you need to go, what you need to do to have a solution be at its solubility, right? Have you added as much salt as you can before it precipitates? Can you add more salt before it precipitates? So what you can do is you can use what is called the ion product, which is Q. And this is going to be defined with a similar expression for KSP for any given solid. So it's going to have that same equilibrium expression, but it's not going to be for an equilibrium. It's going to be for whatever position you want to look at. So it will have the initial concentrations that you use instead of your equilibrium concentrations. You can really plug any concentrations you want here. Typically that's going to be your initial concentrations. So remember, ionic product, which is Q, is going to be the non-equilibrium KSP, right? So you can predict the possibility of precipitation by considering this relationship between Q and KSP. So if Q is greater than KSP, precipitation occurs and will continue until the concentration are reduced to the point that they would satisfy KSP, where Q would be equal to KSP. Q is less than KSP, no precipitation occurs. You don't have enough ions in solution to precipitate. So a solution is prepared by adding 750 milliliters of this salt at this concentration to 300 milliliters of this salt right here at this concentration. Well, CE iodate, which has this KSP right here, precipitate from this solution. So we've been given volumes, we've been given initial concentrations, so we can go ahead and find the concentrations that we were given initially for CE and the iodate. We can then plug those in to generate a Q, compare that to the KSP, and that will determine whether this is going to precipitate or not. Alright, so the first thing we do is we need to calculate the concentration of Ce3 plus initial and the concentration of the iodate initial in the mixed solution before any reactions occur. Alright, so this right here is just using that dilution, same dilution factor that you should remember from Gen Chem 1, that M1V1 equals M2V2, that formula. And so what we do here is the initial concentration for Ce3 plus is going to be the 750 milliliters that we added times its concentration, which is that molarity. We've just represented molarity here as millimoles over milliliters so that the units work out nicely. And that will be then divided by the total volume here, which is the 750 we added plus the 300 that we added of the other solution. We go ahead and do the math here, and we get the CE concentration right here is 2.86 times 10 to the negative third. Alright, so iodate, we do the similar thing. We take 300 milliliters, which is what we added of that, times its concentration over the total volume right here. And that gives us a 5.71 times 10 to the negative third molarity. I would like to quickly point out that the Ce3 plus and the iodate were both factors of 1 to their parent salt. So stoichiometrically, for every one of these we broke up, we would have only gotten one Ce, right? And for this one down here, for every iodate we broke, potassium iodate we broke up, we would get a single iodate out. And so we don't have to deal with any 2 to 1 or anything like that, okay? We just are 1 to 1s. And so we can just directly plug in those concentrations we're given here. All right. So we're going to then look for the ion product, Q. We can get that by, again, using that same, similar as an equilibrium expression, which is right here. And so we plug that concentration in, and that will give us this right here. Where do we get these powers here? Well, that's from this formula. This is a 1. See, there's nothing there. That's 1. This right here is a 3, so that's the power of 3. All right, so we plug these concentrations in that we figured up here in the previous slide. And we go ahead and solve the math, and we get this concentration, this Q value right here. So we then are going to compare Q to KSP. Well, Q is greater than KSP. So what that means is this Ce iodate, it will precipitate from our mixed solution. So some of this will actually precipitate out of our solution because the Q is greater than KSP. And that's cesium iodate. All right. So calculating the equilibrium concentrations after precipitation. Step 1, determine if the product is formed when the solutions are mixed. Calculate the concentration of the ions in the mixed solution to determine Q. Step 2 will be run the reaction to completion. So if a reaction virtually goes to completion when two solutions are mixed, it is necessary to conduct stoichiometric calculations prior to equilibrium calculations. Step 3, allow the system to adjust to equilibrium and determine the concentrations of ions in the solution. Finally, step 4, substitute the expressions derived in step 3 to determine KSP. And so they all have the same sort of setup. Let's go ahead and practice it. So a solution is prepared by mixing 150 milliliters of this and 250 milliliters of this. Calculate the concentrations of Mg2 plus and F minus at equilibrium with solid MgF2. Our KSP for this salt is 6.4 times 10 to the negative 9th. Notice, by the way, that I am always going to be giving you in General Chemistry 2, because that is not a General Chemistry 2 problem if I do not. I will always give you strong electrolytes here. These are all extremely soluble. They will not precipitate in solution. Their solubilities are essentially whatever you want to put in water will dissolve. And so that's never a factor, okay? I know some people get concerned about that. That's not going to be a factor. If I don't give you a KSP like so, then you consider it, you can look here and these are very, very soluble. Okay, so let's go ahead and do this problem. So let's determine whether the solid MgF2 forms. And notice that when we do the work for finding Q, we're actually doing all the work we're going to need later on as well, because that KSP expression is the same sort of thing as our expression for Q, isn't it? So we calculate the concentrations of Mg2 plus and F minus in the mixed solution. Those will be our initial concentrations. This one will be the Mg2 plus. Hopefully you can do this. Otherwise, make sure you go flip back to solutions where we first talked about solutions. If I remember correctly, it's like chapter 4 in this book. Right there is our concentration for F minus. Again, that's just the volume we put in times the concentration over the total volume. All right, now these will be our concentrations initial for our two ions in this equilibrium. Now, we plug those initial concentrations into our expression, which again, where do you get this Mg to the first power? Well, that is just from this salt right here. Mg's 1 and F is to the second power. Okay, we plug the initial values in to get our ion, this Q right here. And that will give us, once we solve for it, 1.46 times 10 to the negative 5. We then compare that to KSP. Q in this case is greater than KSP, and that means we're going to form solid MgF2. So our next step will be to run our precipitation reaction to completion. And so what we do here is we're going to run this to completion to make as much solid as we can here. And so Mg2 plus is going to get used up because that's the limiting reactant. F minus is not going to be completely used up because that is not the limiting reactant, that's the excess reactant. And so this right here is going to be left after this reaction runs to completion as 0 concentration, 0 millimoles. This one right here was 25 millimoles. It'll be minus 2 times this Mg2 plus number, because again, you use 2 F minuses for every Mg2 plus. And so that is then 22 millimoles after we run this reaction to completion. And so we have excess F minus that remains after the precipitation reaction goes to completion. That concentration of that excess F minus would be 22 millimoles divided by the total volume 400 milliliters, which gives us this number right here. So we have assumed right now that the Mg2 plus would be completely consumed, but we know that this Mg2 plus won't be 0 at equilibrium. What we're doing is we're setting ourselves up to do a solubility equilibrium problem, just like we did in the previous example, where we start with none of the Mg2 plus, and then we see how much dissolves. We just are going to start with some initial concentration of F minus, right? That's the only little difference. So we can go ahead and compute now this equilibrium Mg2 plus by letting the Mg2F redissolve to satisfy our KSP. So how much MgF2 will dissolve in this 5.5 times 10 to the negative 2 sodium fluoride solution? That's what we've made this problem into. We have reframed this problem to make it simpler. So we look here, this is the MgF2 dissolving in water, and that's our equilibrium reaction. This would be our equilibrium expression, and that right there is our KSP that was given to us. We do this as a normal ice problem. So we're going to go ahead and take, well, Mg2 plus, we consumed all of that, we said, and so that's 0. The F minus starts with this concentration that we left behind, that excess F minus. The equilibrium concentration, therefore, is going to be whatever we make for the Mg2 plus. The F minus will be the initial plus 2 times what we make of the Mg2 plus. Because again, for every 1 Mg2 plus you make 2 F minuses. Okay, so now we're going to go ahead and plug these equilibrium concentrations into our expression like we have done every other time. And so X there, and this right here is this right here. Okay, now again, we have a value plus 2x, don't we? This KSP is a very small number. And so this 2x, you would expect this to also be a very small number. And so we can go ahead and just assume this 2x is meaningless, leaving us with this right here. We solve for x. We get x equals 2.1 times 10 to the negative 6 molarity. And x would then be the concentration of Mg2 plus. That's what we set it up as, right? All right, so that will be our concentration of Mg2 plus. The F minus, now we could add this number to this, but it'll just get rounded off. So our F minus really is just the concentration, our initial concentration. We don't make enough from this dissolving of the MgF2 salt to even make this number go and do anything, to change it all. So there we go. That is how you do these problems. This is a great example of setting things up to make your life easy. Okay. So selective precipitation. Now this is actually a very old analytical method that was started. People started using this about 400 years ago. And if we go before chemistry was called chemistry, or even natural sciences and is called alchemy, this was probably honestly used. There are records in China of people using selective precipitations 6,000 years ago. So this has some serious history to it. All right, so the selective precipitation, this is a method that's used to separate mixtures of metal ions in aqueous solution. It involves using a reagent whose anion forms their precipitate with only one or a few of the metal ions in the mixture. This is how people used to get like um, changing lead into gold, that sort of stuff, or in alchemy. They would precipitate out a gold ions, then they would use flame to get rid of they'd precipitate out the gold cations using an anion through selective precipitation. They would then usually use a flame, fire, to get rid of the anion. If I remember correctly, the most common one was like cyanide. That's why a lot of them poison themselves. But anyways, it's beside the point. It's kind of an interesting side note, but not much of a actual use. Uh, if you are curious about actual use of this, I did have somebody use selective precipitation and do the process to recover gold from different circuit boards and that sort of stuff. And he made about, I believe he said he made about $60, $70 from, a few hours of work. So, that actually could be pretty good. And people do that actually. A lot of chemistry professors will actually do that. I know a number of them that actually recover gold as like a side little venture. Anyways, um, consider a solution containing Ba2 plus and silver ions. So we add NaCl to this solution. The result is that silver chloride will precipitate as a white solid. Barium chloride, on the other hand, is soluble. So the barium will actually remain in solution. So you can selectively then precipitate the silver out, and you could do something else with the silver. This is actually a very similar example to what I gave you before with gold. That's actually how he did it, and then he used flame to get rid of the chloride and reacted it away. All right, so as chlorine gas, if you're curious. So this example right here, a solution contains 10 to the negative 4 molarity copper and 10 to the negative 2 times 10 to the negative 3 molarity lead. If a source of iodide is added gradually to the solution, will the lead or the copper precipitate first? So specify then the concentration of iodide necessary to begin precipitation of each salt. Okay, so the first thing we need to do is we need to look at these expressions to see, are they similar enough that we can just compare them directly, or do we have to do anything special? Okay, so this right here is the lead iodide PbI2. This would be the KSP expression right here. And you see again, that's just the first power because that's first. That's the second power, so that's second. So the lead in this solution is known to be 2 times 10 to the negative 3 molarity. The greatest concentration of I minus that can be present without causing the PbI2 to precipitate can be calculated from our KSP right here. You literally just can plug this value in. So we go ahead and plug that value in. That's going to give us our greatest concentration of I minus that would cause precipitation. And so that is going to, then we solve for I minus, and we get 2.6 times 10 to the negative 3. So any I minus in excess of this concentration, even if it's one molecule, will cause a solid PbI2 to form given enough time. Now we can do a similar thing here for copper iodide. You will notice that these formulas are not similar enough to be able to compare their KSPs directly. So please keep that in mind when you're doing these problems. I know a lot of you want to cut out a lot of work and you want to just compare the KSPs and say this is what precipitates first. That only works if they make the same number of ions when they dissociate. And these do not. So here we see their KSP expression, and And we can go ahead and plug this concentration for the copper ions in, solve for iodide again, and that gives us a concentration of iodide of 5.3 times 10 to the negative 8th molarity. And again, that's going to be any excess concentration of this will cause solid copper iodide to form. And so we see that the copper is going to end up precipitating first, because that's the one that can take the least amount of iodide concentration before it precipitates. Whereas the lead will precipitate next, afterwards. So the first one to precipitate would be copper. This would leave the lead behind if we put this reagent in. All right, now, and that, by the way, also solved our concentrations part of the problem from our KSP expression. So we've actually done everything by doing that work. I know that it's tempting, and it would have actually worked here if you use these KSPs, but I'd actually recommend you not get in the habit of doing that if you see these formulas are different, okay? Again, if these formulas are the same, where it's one iodide, sure, go for it. You can use those KSPs and directly compare. Please just be careful. You need understanding. This again is another exercise that you guys don't really need because I gave you practice problems now. So selective precipitation of metal sulfide salts. The metal sulfide salts differ in solubilities. So the sulfide ion is used as a precipitating reagent to separate different metal ions. This is fairly common, actually. The advantage of this is sulfide ion is basic in nature. So its concentration can be controlled by regulating the pH of the solution. You can add acid or base to change the concentration in your sulfide ion, which gives a nice control mechanism and lets you actually redissolve the solids later on if you want to further separate them, which is very nice. So this is a great qualitative analysis typically, and this is going to involve separating the common cations into 5 major groups on solubilities. So your individual ions are then identified from each of those groups. So group 1 will be the insoluble chlorides that you can separate things into. Group 2 would then be the sulfides that are insoluble in acid solution. Group 3 would be the sulfides insoluble in basic solution. Group 4 would be the insoluble carbonates. And group 5 would then be the alkali metal and ammonium ions. Keep in mind that your group 5 alkali metal and ammonium ions, these are extremely soluble with pretty much any anion, okay? So these are stuff that is almost completely soluble. It's very, very hard to make those insoluble. So the insoluble chlorides, there's actually a relatively small number of insoluble chlorides. That's why it's group 1, and because it can eliminate things to a actually very relatively small category. And so after adding dilute HCl to a solution that contains a mixture of these cations that you're trying to separate, common cations, you are going to have silver, lead, and mercury will precipitate as insoluble chlorides. The other chlorides, except for silver, lead, and mercury, are soluble, so they'll remain in solution. And so you would then remove the precipitate that happened from group 1, and the remaining ions will then be treated with the sulfide. That same test tube, after you remove this solid, is going to be treated with the sulfide and go into group 2. Literally the group 1, 2, 3, 4, 5, these are the steps you would normally take as you do this qualitative analysis. This is the stereotypical qualitative analysis that you can change a few little steps here and there, but overall, this is going to give you the best bang for your buck. Group 2, sulfides insoluble in acid solution. So remember that your current solution is actually acidic because you already had HCl in there, right? So the solution will be acidic already. You're now going to put sulfide in there, which is H2S, is the most common sulfide you would use here. So when you add the H2S, the highly insoluble sulfides will precipitate due to the low concentration of S2 minus. And so the ones that are extremely insoluble will first come out as a solid. The soluble sulfides will remain dissolved, and the precipitate of the insoluble salts can then be removed. And so you remove the precipitate of the insoluble salts, you collect them up into another container that you can do further testing on, and you leave behind the stuff that's still dissolved for further testing in group 3. So group 3 is then in a basic solution. So hopefully all of you, when I said in a basic solution, went, oh, you added base. Yeah, pretty much. The solution is basic. When you do this, you would typically add a base to it at this point. More HS is added. That is basic. You can actually, assuming you didn't go crazy, let me make a note here that will help you out in lab. So when you do tests like this, qualitative tests, don't go insane and put a bunch of HCl in there and just squirt milliliters and milliliters in. Make sure you're always just put enough. Don't put huge amounts in. If you're going to start by trying to do a reaction, start small. If you're going to start by doing a qualitative analysis, start small. Okay? So assuming you did not go crazy in this step, group 1, group 3, when you add more H2S, you're going to start finding more of these precipitating out as you add more H2S. H2S is actually, sulfide, is actually a base. This will make it more basic. The cations that precipitate as your sulfides increase are going to include things like cobalt, zinc, Mn, Ni, Fe, Cr3+ and aluminum 3+ ions will precipitate as the insoluble hydroxides actually. They don't precipitate due to the sulfide. They precipitate due to the fact that it's basic. Unlike these that precipitate due to sulfide. So you again are going to collect up your precipitate, the solid at the bottom, and you would have again the solution remaining. The dissolved components still remaining. Alright, so group 4 would then be the insoluble carbonates. So all ions except those from groups 1A and 2A of the periodic table would have precipitated at this stage. The only ions that you can still have in that solution are going to be the metals in group 1A and 2A. Or I should say the metal cations in group 1A, 2A. The group 2A cations form insoluble carbonates. So these can be precipitated by adding carbonate to the solution. And so what you do next is you'd add a carbonate to the solution, and you would then see the group 2A cations precipitate out. You would collect those precipitates, leaving the clear supernatant behind. Supernatant meaning the dissolved components. By the way, the most common way of collecting up the solid in these is actually by using a centrifuge. You run the test tubes in a centrifuge, it collects the solid on the bottom, you pour off the supernatant, the dissolved components on the top, and then rinse that solid pellet at the bottom and pour that rinse off. There you go. You have your solid. Alright, so group 5 is going to be your alkali metal and the ammonium ions. These are the only things that should still be dissolved at this stage. The ions will form soluble salts with common anions. These are just incredibly hard if you wanted to try to form the precipitate with these. So these will be the ones that remain. You have to typically use different methods, usually, we'll talk about electrochemistry later. Electrochemistry probes that we'll talk about later are a great way of separating these. And honestly, they've mostly supplanted this entire method, but they're very expensive and they can be somewhat finicky, whereas this method is very, very reliable. Okay, so the next thing we're going to talk about is the second part of that name of the chapter I gave you, which is the complex ion equilibria. So a complex ion, the name actually says everything you need to know about it, which is a charged species consisting of a metal ion surrounded by ligands. A metal ion surrounded by ligands is commonly called a complex. So it's literally just an ion that is made by a complex of a metal and ligands being things that are attached to the metal. Ligand, the exact definition is a Lewis base, by the way. This is a molecular ion that has a lone pair that can be donated to an empty orbital on the metal ion to form a covalent bond. So they'll form one or more covalent bonds with the metal ion. And these are always going to have what's called a coordination number. This is the number of ligands that's attached to a metal ion. And that tells you how many times they'll attach to the metal ion. So these will have a formation or stability constant. This is like an equilibrium constant. It is an equilibrium constant. And what it is for is each step of a formation of a complex ion by the addition of an individual ligand to a metal ion or complex ion in aqueous solution. Usually the total concentration of the ligand will be larger than the total concentration of the metal ion. One of the things I would like to point out at this point is I know many of you are probably starting to blur your eyes and sort of tune out my voice because for the most part I find people find this portion of the chapter incredibly boring. And most people go, why should I care? This is actually proteins, guys. Okay? This right here, what I'm actually talking about, is the basis of which you're going to build up your knowledge and ability to deal with proteins if you go on to biochemistry, or really in almost every biological or medical career, you're going to have to know something about protein binding. These are all the things. So ligands are actually proteins. Most proteins are ligands, and they will bind to metal ions just like this. When we talk about an enzyme substrate complex, which you guys may encounter later on in your careers, this is what we're talking about. This is the same information. So if you understand this, when you reach that biochemistry portion, you have to start understanding a bit more complex. It won't be a reach for you. It'll be very simple, actually. It'll be quite obvious from this information. So let's go ahead and try a problem with this. So let's calculate the concentrations of silver Ag plus, the silver complex AgS2O3 minus, and the other silver complex which just has two of those S2O3s attached. Notice these are all charged, so these would all be soluble in solution. That's the interesting thing about complex ions, is they are charged, they're soluble in solution, they're not like the solid that would precipitate. So any solution prepared by mixing 150 milliliters of this and 200 milliliters of that. So right here what we have is we have a stepwise formation equilibrium of these different complexes. So the first one right here is this complex here, and that's going to be formed from silver. And this S2O3 polyatomic anion. Now the next one is going to take this, that's going to be the reactant, and it will add another S2O3. And again, that will form our final complex here. This is going to have a K1, that's for adding the first S2O3, and a K2 is going to be for adding the next S2O3. Okay, you may notice this is very, very similar to the sulfuric acid polyprotic problem we did before. Uh, it is. It's just like that. We're really doing the same sort of thing. We just do it stepwise, just like we did there. Okay? Yes, it's exactly like that. You're on the right track. Okay? All right. Now, your concentrations of your ligand and metal ion and your mixed solution before any reaction occur are going to be these right here. And again, we just took the initial volume times the initial concentration over total volume. We got our concentrations here. Notice that again, like we had mentioned in the earlier statements, the metal ion is typically much smaller than ligand. If you don't do this, the ligand typically needs to be a much larger volume, much larger concentration than your metal ion for significant binding to occur. So our ligand is a much larger concentration than our silver, right? The K1 and K2 are both fairly large. So the formation reactions can be assumed to go to completion. So in this case, the net reaction in the solution will be as follows. We will have our silver completely consumed. So that will go to completion. And how do you know these are going to go to completion? There's two ways you look at this. The K's, if these are tens of thousands, so this right here is like 39,000, then that would normally indicate the equilibrium it greatly favors product, right? And then we look at these concentrations, and that's a factor of 10,000 again. If you have a factor of 1,000 difference between these two, you can assume that this is going to completely use all of this. Okay, and so we're going to consume all of our silver. That concentration isn't large enough to really affect our ligand here, and so that essentially stays the same concentration. And our complex is going to use up, well, all of our silver. And so in this case, 4.2 times 10 to the negative 4 is what we're going to produce of that final complex. So the Ag plus, this is limiting. The amounts of S2O3 that's consumed is negligible here. All the species are in the same solution, so the molarities can be used to do the stoichiometry problem. We don't need to worry about converting them into millimoles or moles. The concentration of Ag plus is not zero at equilibrium, and there is, of course, some Ag S2O3 in the solution as well. So we have, of course, assumed things. So let's go ahead and try to calculate the concentrations of these species, because there's going to be some remaining in there. It's just the vast majority is going to go into the form of the Ag S2O3 2. So let's calculate the concentration of the Ag S2O3 from our K2. So again, this is our K2. This right here is our concentration of this AgS2O3 from our K2 equilibrium expression. And this right here is going to be our concentration of that S2O3. Again, remember this did not significantly change from creating this. This was just too small a number. This means that this leaves us with this one value that we can solve for. So we take this, divide by this, we multiply that over, then cross divide, and we're left with 3.8 times 10 to the negative 9 molarity. Alright, so we can then calculate our silver ion from the K1. So now we have all of these other values except for silver. So we've made ourselves up for an easy problem. So again, our silver complex right here is that number we just got. This, of course, doesn't change because these numbers are so dang small, they don't matter. And so again, yes, we have that. And here again, we have our silver, which is what we're going to solve for. And that gives us our silver concentration of 1.8 times 10 to the negative 18 molarity. So the results show that our final complex right here is vastly larger concentration than this, the middle complex, the 1s2o3 complex, and that is much, much larger concentration than the silver ion in solution. So our assumption was valid that essentially all of it goes to this form right here. Now, you may be going, well, Dr. Clausen, why didn't you do the plus x, minus x sort of stuff here? Again, this number is going to be so small. That x right here is going to be so small that it's not going to change these two numbers at all. So whatever you have left of this isn't going to affect these at all. All right, now the complex ions and solubility. So the ionic solids that are nearly water insoluble must be dissolved somehow in aqueous solutions. So when the various qualitative analysis groups are precipitated out, the precipitates must be redissolved if we want to further separate those ions within each of those groups. So how can you do that? Well, some of the strategies for dissolving water insoluble ionic solids are going to center around these complex ions. So if the anion of the solid is a good base, the solubility is greatly increased by acidifying the solution. Essentially, you're going to be taking out that anion and making an acid out of it, right? Just like we had talked about before with things like F minus, you had an acid that will create HF, which means they'll push it towards dissolving. When the anion is not sufficiently basic, if it's not a reasonably strong base, the ionic solid must be dissolved in a solution containing a ligand that will form a stable complex ions with its cations. By the way, many shampoos and various different consumer products actually make use of this strategy using a ligand called EDTA. If you're ever wondering. So yes, this is something commercially done as well. Oh, and this actually is something commercially done as well. If you're ever wondering, like, you may have noticed that you get buildup, a carbonate usually buildup around like your shower heads. If you take an acid and soak that shower head in a weak acid like lemon juice or vinegar, usually you want to use a bit diluted, usually like at most 50-50 is what I'd recommend, but you can also buy it from like supermarket and stuff, specifically designed for that. So that what those are is those are acids that the anion in those cases where you're looking at a shower head is typically carbonate. And so that acid will actually react the carbonate away. And in that case, it actually makes CO2, which is why it bubbles. But it also reacts some of the other anions away as acids. And yes, you're using this property right here to actually dissolve the scaling on your shower head, the carbonates that are on your shower head or water tap. So some of the other strategies for dissolving these, some insoluble solids have to go through a combination of reactions to be dissolved, in which case you would have to do a series of reactions to get them to dissolve. The solubility of many salts will increase with temperature, so sometimes it's just good enough to put them in water and simply heat it. And that will make the salt sufficiently soluble to make it dissolve. Some of them are only insoluble because it's too low temperature. A great example of this is, of course, Epsom salt, right? Okay, folks, you take care. Good luck, and I will be getting to the next one tomorrow afternoon.